All right, so pretty much everything you guys have done so far is in the rectangular coordinate system. So that is the regular XY plane. In this, your points are going to be labeled XY, right? This is also called the Cartesian plane, named after Descartes, who was like the first person to really use it. So that is pretty much all you've known as far as graphing things go. So the polar coordinate system is going to be a new system that we are going to learn. And the polar coordinate system uses an angle and a radius to locate each point. So the points are going to be labeled R theta there. And so polar coordinate systems actually have a lot of application in real life because they are very applicable to things like sea and air navigation. Because, if I am, walking to the back of the room, I'm going to be on a coordinate, like an XY coordinate system, more or less. I can go, especially with them in rows, right? I got to go this way, and then I got to turn, and I got to go this way, right? I'm just pretty much going like up, down, left, and right, if you think of it as the coordinate system. But if I could fly, then if I needed to get to the door back there, right, I would just go straight there, right? I would turn towards the door. That'd be my angle, and then I'd go as far as I need to go, right? So that is how the polar coordinate system works. You go straight to the point, no like right or left first and then up or down. Whenever, I think it's when we went to Charleston, we went to like the battleship thing, I think in Charleston. I don't think it's Savannah. I think it's Charleston. Which is the coolest. I thought it was going to be super boring, but it was really cool, and I loved it. Y'all should go sometime. But in their like navigation like area, they just had like huge charts that looked just like this. I took pictures of them. I was like, oh, those are polar coordinates. So it has a lot of application because if you can fly, or if you're in the ocean, you don't have to go on roads, right? You just go straight to where you're trying to get. In the polar coordinates, the absolute value of R is the radius of the circle. The absolute value bars are there because we're going to be able to have a positive or a negative radius, which will tell us whether we're going like towards or away from the angle. So we'll see that when we get into this. And then theta is your angle in standard position. And standard position just means it's like your unit circle angles where your vertex is on the origin, your initial side is the positive x-axis, and then your terminal side is your other angle there. Plotting polar coordinates is not too bad, right? If I have something like pi over 3 as my angle, I'm going to go over here to pi over 3. And then on your polar graph paper, whatever type that you have, you are going to have all these circles. And you'll notice that it is labeled like here, 1, 2, 3. You can still think of this as like your x and your y coordinate, x and y. So like right here's 1, here's 2, here's 3, here's 1, here's 2, here's 3. But rather than going over 1 up 2, we are going to pick an angle and just go out that distance. So like pi over 3, 2, I'd go to pi over 3. Also notice right here that polar graph paper is going to have some pieces that we don't have on the unit circle. So right here is pi over 6, right here is pi over 4, right here is pi over 3. It also has these little pieces right here because it has put them on there evenly. So that is pi over 12. If you need to know it, you're pretty much only going to be asked to do unit circle values. Just be careful and don't let like these little pieces right here mess you up on those. So pi over 3 right here. You're going to start right here from what we would normally call the origin is called the pole in polar coordinates. So we start from the pole right here, and we're going to go out 1, 2. And so right here would be my point A. So if I want to graph 3 pi over 2, 1, well, it's 1, 3 pi over 2, but I always think of the angle first whenever I'm doing this. So 3 pi over 2 is right here. So you can see that unit circle is still not gone away. You pretty much need to know all of that stuff. And then you're going to start at the pole right here. You're going to go towards that 3 pi over 2, just one circle this time, and there's your B. Next, you've got 4 pi over 3. So 4 pi over 3 is right here on that unit circle. So we are going to go out 1, 2, 3 right here. So there's our C. For D, we've got negative pi over 6. That's not a unit circle value, but we can just think about going, instead of going pi over 6 in the positive direction, we just go in the negative direction. So right here is negative pi over 6, and we've got a radius of 2. 1, 2, right here. So there's point D. There will be values that are not whole numbers. If you're just being asked to graph a point, probably not. They'll probably be whole numbers just because that way you can be precise about what you're doing. When we start graphing like polar equations, we'll definitely see some where we got to kind of guess. So like if there was another one, if they told you like F was at, let's say 2.5 pi, we would just, pi is right here, and then we would go out 1, 2, and then you're going to go halfway between 2 and 3, so you'd be like right here for that. So you may see some that fall in between, but if they're testing you on it, probably whole numbers for that. Okay, so let's look at example 2. He has put example 2 here for a very specific reason. We've got 2 pi over 4, so we're going to go right here at pi over 4, and we're going to go out 1, 2. So that would be right here, and that will be A. All right, then we've got 2 negative 7 pi over 4. Where is negative 7 pi over 4 going to be? It's the same as pi over 4, right? Like if you need to, you can do negative 7 pi over 4 plus 2 pi, which is going to be negative 7 pi over 4 plus 8 pi over 4. That's going to give you 1 pi over 4. So it's a different angle, but it still has a radius of 2. Where's point B going to be? It's the same place as A, right? Same place. Okay, what about 9 pi over 4? It's the same place, right? Because 9 pi over 4, if you subtract 2 pi, which is 8 pi over 4, you're going to get pi over 4. So it's also here. Let's think about D. I feel like it's going to be the same place because he's really starting a trend here, right? But it's a little bit different on this one because we haven't seen any yet that have a negative radius. Okay, so when that radius is negative, when you have a positive radius, you go towards the angle. So everything so far we've gone out towards the angle. If we have a negative radius, we want to go away from the angle. So here's what that looks like. 5 pi over 4 is right here. I'm going to use my highlighter, and I'm going to highlight that line for 5 pi over 4. And then I'm going to keep on going and go all the way across the circle, right? Make myself a line right there. So when you have a negative radius, what it's telling you is to start at the pole, and rather than going towards 5 pi over 4, which would be like this point right here, we're going to start at the pole right there and go away from 5 pi over 4. And if I do that, out to right here, still at the same point, right? All 4 of those points are at the same location. So, polar coordinates are going to be a lot different than rectangular coordinates. Rectangular coordinates only have one way that you can define a point. So, you can only say that this point is at 2, 3. There's no other way to say it. But polar coordinates have an infinite number of ways that you can give that same value. Questions? Mm-hmm. I usually do. Yeah, I look at that like that y coordinate, that angle first on these, because that's going to tell you which direction to go, and then start from that pole and either go out towards that angle if it's negative, or if it's positive, and if it's negative, you're going to go towards away from the angle. There. Yeah. So like you're going to think about if you have a negative radius right here, then you're going to think about, well, 5 pi over 4 is here. I think about like highlighting that whole line right there. And so rather than going towards 5 pi over 4 like this, out this way, if you have a negative radius, you have to go away from 5 pi over 4, which gets you to that same point there. We are supposed to plot the point with polar coordinates 3, 5 pi over 6 on the polar grid above, or I should say to the left. I didn't change my wording whenever I was rewriting this. Then write polar coordinates for the point 2 different ways. There are infinite ways, so you could have infinite answers here. But let's graph 3, 5 pi over 6. So 5 pi over 6 is right here, right? And then we've got 3, so we're going to start at the pole right here. We're going to go out 1, 2, 3. So right here is the point that we're looking at. Yes?
Oh, wait, is there a line in between pi over 6 and...
The polar graph paper that you will see is going to have, like, right here is pi over 6, right here is pi over 4, right here is pi over 3. Those are the ones we have on the unit circle. It is going to have these additional lines right here, because what they have done is they want to count by like equal increments. So it's pi over 12 is what it is. So it feels like it should be down here, but it's not. That, like, this is pi over 12. This is 2 pi over 12, 3 pi over 12, and so on. So it's going to have these extra lines there that aren't usually on our unit circle. So be careful with that. There. So this point right here, we need to write in 2 different ways. So there are an infinite number of ways I can write that angle. Right? I could just add or subtract 2 pi as many times as I want. So that's an option. I could add 2 pi. I could subtract 2 pi. The first one I want to look at, though, is using a negative radius, because I think that's interesting.
Could you do negative 3, 11 pi over 6?
Yes. Because if I take this line right here and I extend it out all the way across, right, it is across from 11 pi over 6 right here. So if I do negative 3, 11 pi over 6, that means that I would be thinking about 11 pi over 6 here, but I go away from 11 pi over 6, so I'd go backwards 1, 2, 3, which would also get me to that same point. So you could, to use a negative radius, you can do that. We also could just change our angle, like 5 pi over 6. We could add 2 pi or subtract 2 pi. I'm going to subtract it. So if I subtract 2 pi, I would have 5 pi over 6 minus 12 pi over 6. You got to get those common denominators. That's going to be negative 7 pi over 6. So 5 pi over 6 and negative 7 pi over 6 are coterminal angles. They would have that same position. So I could do positive 3, negative 7 pi over 6. There are others here that you could use for sure. Instead of 11 pi over 6, you could use negative pi over 6. You know, they can just go on and on and on. Okay, questions there? Now, the next part, the polar coordinate system can be like placed on top of the, it can be like placed on top of the rectangular coordinate system. They are the same, sort of, because where we see this counting as 1, 2, 3, that can still be like our x and our y axis, right? But instead of drawing rectangular lines, we're drawing all these circles out instead. In fact, if you look at Desmos, you guys probably did this in Math 3 to help you cheat on your unit circle stuff a little bit. If you hit the wrench over here, you can change Desmos to a polar graph. Now watch what happens right here. Like if Desmos really only graphs, Desmos, as far as I know, really only graphs like rectangular coordinates. We cannot get it to graph polar coordinates unless there's something new that I have not learned about yet. Because if I graph like 2 pi over 2, it does not put it where it's supposed to be. Right? Pi over 2 is right here. That's not. Like if I graph that, I go polar. That's not at pi over 2. It does not graph polar coordinates. It will graph rectangular coordinates. So if I like graph let's do 0, 2. If I graph 0, 2 right here, it will graph it right here on the coordinate plane, right, 0, 2. But if I change it to polar, I could also call that point 2 pi over 2 in polar coordinates, right, because I'll be going towards pi over 2, and it would be 2 right here. I don't think you're really going to, well, you might get a couple multiple choice questions that would be on calculator active where this would be helpful. But whenever Desmos switches back and forth, it's not moving that point. It's just changing the background, right? So they're sort of on top of each other right there. So rectangular coordinates can be converted to polar coordinates. So like if I think of graphing the point x, y, that means I start at 0, 0, I go over x, I go up y. If I graph polar coordinates, I don't do that. I turn a certain angle, and then I go out a certain radius. Well, if I put those two things together right here, I just get a beautiful right triangle right here, right? In fact, we've kind of worked with this a lot with a lot of the trig stuff that we're doing. So we already know, if I want to know cosine of this angle right here, cosine is adjacent over hypotenuse. So cosine would be x over the radius. So if I want to solve that for x, so I just have like a formula for converting here, all I would have to do is just multiply by that r on both sides. So x just equals the radius times cosine of theta. We've really kind of already done this with some of our unit circle stuff, right? Because whenever we had those problems on the unit circle, or well, not on the unit circle, they were on circles with radii that were not a unit, right? Then we basically just had to take our unit circle value, our x coordinate, and multiply it by that radius. This is the same thing here. It's really not anything new. Sine is similar. Sine is opposite over hypotenuse, so that's going to be y over r. So if I do the same thing there and multiply both sides by r, then I would just have that my y equals r sine theta. So polar coordinates can be converted to rectangular coordinates and vice versa. So let's start with taking polar coordinates and turning them into rectangular coordinates. So if I have 2 pi, my x-coordinate is going to be the radius times cosine of pi. And testing our unit circle again here, what is cosine of pi? -1. So I get -2. And then my y value is going to be 2 sine of pi. And sine of pi is 0. So it would be 0. So my rectangular coordinates for this point would be -2, 0. Okay, so do the other two for me there. You should get 2, -2 root 3. You might have -4 root 3 over 2. That 4 and 2 can just reduce to make it a 2 right there. And then C, you should have 3 square root of 3 over 2 and 3 halves. And let's look at this on Desmos so we can see what's going on here. To be able to tell what's happening. So if I graph, Desmos will not graph polar coordinates, or it won't graph them correctly. It'll put a dot there, but it'll be wrong. But it will graph 2, -2, square root of 3. So if I graph that point, and then I change my background to polar coordinates, you can see that I am at, let's zoom in a little bit more, there we go. I am at 5 pi over 3, and I went out 1, 2, 3, 4 on those circles, right? So you probably are not going to have the calculator on a problem like this on a test, but if you need to check yourself just working through your homework, you can definitely just graph it and see, change your background right there. If I graph the other point, 3 square root of 3 over 2 and 3 halves right here. Now this looks like it is 3 pi over 6. But it was 7 pi over 6, which is over here, right? And instead of going, because you have a negative radius, instead of going towards 7 pi over 6, you go away from 7 pi over 6, which would be 1, 2, 3, right here at that green dot, right there. So these are correct. Okay, questions? So those formulas are really formulas that we kind of already know because we've used it on the circle stuff that we've already done, but you want to know them because they will make your life much easier on figuring those out. We're going from rectangular to polar. It is a little bit more difficult, but still some pretty basic math that we'll be doing. So if I know theta and r, so if I know the angle and the radius, and I'm trying to find if I know x and y, and I'm trying to find the angle and the radius, if I know x and y, and this is a right angle right here, what can I do to find r? X squared plus y squared equals r squared. So Pythagorean theorem, x squared plus y squared equals r squared. You can just set up Pythagorean theorem for finding that radius. So pretty basic stuff right there. For the angle, if I know x and I know y here, that is my y is my opposite side, x is my adjacent side, I could set up tangent for that. So tangent of theta is going to equal y over x. We also already have done that some, right, from our circle stuff. And then I would go ahead and solve that for theta so you have inverse tangent, but you have to be careful with that because if you use inverse tangent, it restricts it to only half of the circle, and it could possibly be the whole circle for that. So let's do one of these problems. What I would suggest is draw yourself a graph so you can make sure that it makes sense. Okay, so if you have negative 2, 2, it doesn't have to be an extensive graph. You're going to go left 2, down 2. You got this point right here. You're right. You are correct. Up 2. Left 2, up 2. So you're right here. So you need to connect that point to the origin. And then you're thinking about this right here being your angle. And you're thinking about this right here being your radius. Now, sometimes kids get their triangles a little messed up. You need to drop a line down from your point to make that a right triangle. So this side right here is negative 2. This side right here is positive 2. And so for radius, we're just doing Pythagorean theorem. So we'll do 2 squared plus negative 2 squared equals the radius squared. So that is 4 plus 4, which is going to be 8, equals your radius squared. You will square root both sides. Square root of 8, they're probably not going to leave it as square root of 8 because square root of 8 will break down. What could you break 8 down into? 4 and 2. So this is square root of 4 times 2, and the square root of 4 is 2. So they'll probably do 2 root 2 for that. Square root of 8 is equivalent, but they're probably going to make it 2 root 2 on that. Yes, because the square root of 4 right there, square root of 4 is 2, so it goes on the outside. This other 2, you cannot take the square root of it, so it's trapped on the inside. And so when we're doing our angle here, we're going to do tangent of theta equals opposite, which is 2, over adjacent, which is negative 2, right? Or just do y over x. Same thing right there. So we're getting tangent of theta equals negative 1. Now here's why I highly suggest you drawing yourself a picture. Because there's a few places where tangent is negative 1, and if you just rely on doing inverse trig, you're going to get the wrong quadrant. What quadrant is our point in? Second quadrant. So we need an angle that's going to be in that second quadrant, right? So tangent, where does it equal 1, negative 1, in the second quadrant? At 3 pi over 4. So our angle is going to be 3 pi over 4. Tangent also equals negative 1 at 7 pi over 4, or negative pi over 4. But that's not the one you need for this because you need to be in the second quadrant. So we would have our point here is going to be 2 root 2 and 3 pi over 4. So if we do B, let's sketch ourselves a little graph. We got 1, negative root 3. So, this one's not as easy to sketch. We got 1. We got negative root 3 is not quite 2. You're going to be like somewhere right here. We need to connect right here. There's our radius, our angle. Goes all the way around right there. And then vertical line connecting it to the x-axis there so that we can have a right triangle. This is your x, it'd be 1. The vertical piece is negative square root of 3. So for Pythagorean theorem, 1 squared plus negative root 3 squared is going to equal the radius squared. 1 squared, of course, is just 1. What do we get when we square the negative square root of 3? It's positive 3. Because that negative is on the outside. What you're doing is negative root 3 times negative root 3. So the negative times negative is going to be a positive. So you should get positives on both of those right there. So 1 plus 3 is 4. That's your radius. So 2 is your radius. And then we're going to set up tangent of theta is going to be our y over our x, right? Opposites over adjacent. So negative root 3 over 1. And so tangent's the hardest from the unit circle. I'm thinking, I know I'm over here in that fourth quadrant, and it's either right here or right here. I can kind of tell by the way that it's graphed. Like I don't go over, I only go over a little bit and then I go down more. So I think that it's probably right here. Think about your unit circle. On that unit circle, right here, this point is 1/2 square root of 3 over 2. And tangent is y over x, so square root of 3 over 2 divided by 1/2. Yes, negative right there, you are correct. So I'd get negative root 3 over 2 times 2 over 1. 2's cancel, that is it, right? So we're going to have, what is this angle right here? 5 pi over 3. So our coordinate is 2, 5 pi over 3. You're just kind of guessing on that. The square root of 1 is 1, and the square root of 4 is 2. 3 is between 1 and 4, so you know it's somewhere between 1 and 2 there. And really, as long as you have it in the right quadrant, even if you do pretty bad at guessing on where it's at, you should still be able to tell where it's gonna, where your point is gonna be. I think if you get coordinates that are on the x or y axis, they're a lot easier to do. I don't usually set it up for those because I've got 0, negative 5. So 0, negative 5, you know, if I'm graphing that, 0, 1 is right here. So just think about drawing yourself a circle. What's the radius of that circle? It's 5, right? And what's your angle right there? 3 pi over 2. So I've just got 5, 3 pi over 2. It will work to use your formulas. The problem is that you can't really draw a triangle for that, right? So, but really they're the easiest problems if you just draw it out and think about, it's either at 0, pi over 2, pi, 3 pi over 2 there, and whatever distance you've gone out is your radius for that. So Desmos will graph your rectangular points correctly. Yeah, so like on this, if I graph, now a lot of these will not be calculator active, so we can't rely on Desmos totally to do it. But if it does show up on calculator active, I could just graph 0, -5, which is here on my regular coordinates, and then change my background to the polar coordinate background, and I can see on it 3 pi over 2, I went out 5 for that. So if you graph the rectangular coordinates and then change your background to polar, it should give you the right thing. But if I try to type in, try to type in 5, 3 pi over 2, it's not going to graph that correctly. It can't graph the polar coordinates for that.
So are the rectangular and the polar coordinates, are they like basically the same values, just expressed in a different way?
Yes, they're the same, like they're still the same point on your regular XY coordinate plane, but they're the way that you're getting there is different for that. But like it's more or less like the way that you're talking about the point, not where the point is at. It's changing.
Does that to find the radius for like any of these polar coordinates? Is it always Pythagorean theorem?
Yes. Yeah. You could even do Pythagorean theorem with the one that we just did, even though it kind of doesn't make sense because it's not a triangle. But if you do it, 0 squared plus -5 squared equals your radius squared, which is 25 equals your radius squared, and you square root both sides. So it'll even work when it's not really a triangle for that. Okay, so we also have to look at this. I'm mostly concerned with you being able to graph polar coordinates and being able to convert back and forth from rectangular to polar or polar to rectangular. We also have to look at how this can be shown on a complex plane, which is also something new that you have not really seen. So complex numbers can be graphed on a complex plane where we've looked at complex numbers before. We've got a plus b times I, where a and b are numbers there. So we've got, like, for example, they use the point 3, 2 right here. 3 plus 2i could be graphed as the point 3, 2. So what is happening there is what we normally think of as our x-axis, our horizontal axis. That is your real number axis. So like that 3 right there is the real number. And then this is your imaginary axis. So the 2 right there gets graphed on your imaginary axis. Okay, so to me it feels a little random to be throwing this in right here, but it's in what we've got to learn. We also need to be able to graph imaginary numbers on polar coordinates. So get ready right here. It's mostly a formula. It's not that bad, but it seems a little crazy. So we know x equals r cosine theta and y equals r sine theta. So using these identities, if a complex number has polar coordinates, it can be expressed as r cosine theta plus I r sine theta. So like your y coordinate here, where you can almost think of right here where we've got 3 plus 2i. This is like your x plus y times I is sort of what you're graphing there. So, well, if we replace x with r cosine theta and y with r sine theta, now we can also do this with complex numbers. So the types of questions that you might see will look like this. A complex number is represented by a point in the complex plane. The complex number has rectangular coordinates, -2, -2. What is one way to express the complex number using its polar coordinates? Okay, so essentially what you are doing here is just turning this into polar coordinates and then using this formula right here. So, like currently, this complex number using rectangular coordinates would be -2 minus 2i. We really just need to change our -2 to polar coordinates right here, and then we'll sub those in, right? So x is going to equal the radius times cosine of theta, and our y is going to equal our radius times sine theta. So we're going to need to find the radius, right? So if I think of graphing this, -2 is right here. There's that radius, and then like this side is -2, this side is also -2. Here. Okay. So for that, we need to do Pythagorean theorem. So we got -2 squared plus -2 squared. We really already did this once. That's 8 is your radius squared. So you're going to square root both sides. We could simplify that 8 to 2 root 2. So that's our radius. And then our angle, in this case, we're going all the way around here, tangent of theta is going to be -2 over -2, so 1, right? And where does tangent equal 1 in that third quadrant? Those are the coordinates. I need the angle. Good, 5 pi over 4, so x, 5 pi over 4. So, for this, our polar coordinates could be expressed using this expression. I'm going to be honest, I don't even know why you need to do this. I don't know where this is useful in life, but Mr. Passwater put it in here and he knows more than I do. We're going to do 2 square root of 2 cosine of 5 pi over 4 plus 2 square root of 2 sine 5 pi over 4 times I. That would be, actually I don't really need that. I don't need that. I'm pretty sure if we simplify, we're going to get back to like the -2 and -2, so we don't really want to do that. Again, I'm not 100% sure where this is useful in your everyday life, but probably. It's just your, like, r cosine theta, that is your x, and r sine theta is your y. And so the y is the one that has the I with it, because that's your vertical axis. Your vertical axis is your imaginary axis here. Last question is sort of asking it in a different way. A complex number is represented by a point in the complex plane using polar coordinates. The complex number can be expressed as 4 cosine 7 pi over 6 plus I 4 sine 7 pi over 6. Express the complex number using its rectangular coordinates, x, y. So this part right here is your x. This part right here is your y. So basically I figure it out, right? So on that unit circle, 7 pi over 6 is right here. The coordinates of that point are -√3 over 2, -1/2. So you are going to have your x is going to be 4 cosine of 7 pi over 6, which is your x coordinate, so that's -√3 over 2. And you're going to have, that'll give you -4√3 over 2. Those can reduce, you'll just get -2√3. That's your x coordinate. Your y coordinate is just 4 times that sine value, which is -1/2. So you get -2. So as polar coordinates, as rectangular coordinates, I could have negative 2 root 3 minus 2i. That's what we're looking for here. You're essentially just simplifying this, like you just pull those unit circle values and simplify. And if you graphed it, it would look like the point negative 2 root 3, negative 2 in your rectangular coordinates. Again, don't ask me too many questions about why. I don't have that information. I'm sure there's a reason. I don't know it.
Which one do you need?
I think this is how they want the answer on that. The one I circled. Yeah. Okay, so we're going to have a worksheet.